Hey everyone, my name is Clemens Schaefer, and I'm going to present to you today our work, Edge Inference with Fully Differentiable Quantized Mixed Precision Neural Networks. This work was partially done during an internship at Google with my advisors Shan and Raul Blazquez. We also collaborated with my academic advisor Siddharth Joshi from the University of Notre Dame. The large computing and memory cost of deep neural networks, DNNs, often precludes their use in resource-constrained devices. Quantizing the parameters and operations to low-bit precisions offers substantial memory and energy savings for neural network inference, facilitating the use of DNNs on edge computing platforms. In this work, we are proposing a new quantization approach for mixed precision convolutional networks targeting edge computing. Our main contributions are a method for tensor-sliced learning precision with a hardware cost function for heterogeneous differentiable quantization. Our second contribution is a targeted gradient modification for weights and activations to mitigate quantization errors. And thirdly, we devise a multi-phase learning schedule to address instability in learning arising from updates to the learned quantizer and model parameters. So firstly, to quickly set up our method, we have to define and establish how can we design differentiable neural networks with respect to the bit widths. So essentially, we need differentiable quantization, and this can be done with a differentiable quantization function, which you can see over here. We basically take in a value we want to quantize or a tensor we want to quantize. We have a step size and a dynamic range. And basically, given the step size and the dynamic range here as Q max, we can quantize our values. And if we use the step size and the dynamic range as indicators for how many bits we use, we basically have control about the bit width too. The way we're doing is we're setting up a loss function where we're training on the one hand the accuracy of the network, and on the other hand we're trying to control for the size of the network. And the size of the network is tying in with the number of bits we use per layer. So essentially we have a starting configurations which is giving a certain size, and given that we have a target in size, we can push the size down by adjusting or learning gradients for the step size, or alternatively for the dynamic range. The second contribution we are tying in a little bit here is that in the quantization approach, if we do a rounding, we need essentially surrogate gradients. One of the aspects which is usually done is to say, okay, well, we use a straight true estimator. So we just say basically nothing happens in the backward pass. We figured we could do something better there and looked at various different works and came with some of our own, where we say in the backward pass, when we do rounding, we can adjust the gradient to a certain degree, whether we're close to a quantization point or not. This is illustrated in this figure here, where we essentially see that we have a strict true estimate as a line and various alternatives to check for as surrogate gradients. Moving on, essentially the biggest part we face that during training we encounter instabilities if we start straight up try to train the step size and the dynamic range. We essentially devised a three-phase training schedule. We start out with some pre-training. During pre-training, we actually keep our bit widths fixed. So we keep our step size fixed, we keep our dynamic range fixed, and we're just training the network to have a reasonable level of accuracy, given that we actually quantize. Once we're done with pre-training, we're essentially saying, okay, well, now it's time for to learn our bit widths. So our second part of the loss function, the penalty for the network size, now kicks in. And now every 5 steps, and we determine 5 to be 20, we're updating the quantization parameters. So you can essentially see in this graphic a kind of a deterioration. We see our memory footprint, which is going down, which is good, which is our target. We were trying to reduce the memory footprint by updating the quantization parameters. On the other hand, we can also see that the accuracy to the right curve is going down too. We try to control for it a little bit by figuring out what the right phi should be. We're trying to ramp up the size penalty. So immediately we don't really kick in with the full size penalty. We just increasingly increase it. However, accuracy loss is not fully preventable. At some point it picks up again, but freezing the parameters and then just doing something a third fine-tuning step really improves accuracy performance again. This is roughly our method. And now coming to the results. As I mentioned before, there are various surrogate gradient methods for what can you do in the backward pass with the rounding function. And we were combining various of them for weights and for activations, and we were trying to figure out what is the best one. So a standard method is the straight true estimator, which is the yellow line here. A other common method is like EWGS, it's just like different work, and which is the purple line over here. Our combination, like if we do like a sensible combination, especially like the H configuration or the E configuration, or our favorite configuration, the J configuration, where we use EWGS and like a 10H modified function for the activations, we can yield better results than state of the art. This was one of the points there where we picked, okay, well, we can figure out like a good surrogate gradient function for the rounding function. And additionally, now looking at the space where we trade off error versus like the model size, we could substantially push the Fourier like the Pareto transform, the Pareto curve to the left side. We could reduce evaluation error and model size beyond what other people have done so far. We can see different models here. We have like our standard efficient model quantization. Then we push it further to the right, further to the left with our technique, and the red line then is a different model, which is like the MobileNet model, which it seems to be better for even smaller bit widths. Then the interesting part would be like, let's have a look, actually like a look inside, what is happening inside the model. How do we actually allocate bits? Are there some patterns we can see? Are they doing some kind of like architectural patterns we have? And the interesting part is like, we can see, at least for the activations, we have like those triplet patterns with like very low bit width, very low bit width, a high bit width, which seems to be very consistent like to the EfficientNet and to the MobileNet. And we think this is like tied to like kind of like a high precision path to the network where we have residual connections. And those residual connections, like if we quantize them to low bit widths, they're lost for the whole network. However, if they're kept at high bit widths, like the layers in between, which like can be skipped, they can have lower precision, which we found like a very interesting insight. And that seemed to hold like for the EfficientNet as well for the MobileNet. And lastly, we've done multiple additional studies, but like one thing we would like to point out essentially is that given a sophisticated black box algorithm, just trying to figure out like, okay, well, what should those parameters be? What should be the allocated, like what should be like the right bit width and like the best accuracy? We found that our method actually outperformed it. So like we used a training schedule, which we handcrafted here, where we said, okay, well, this is like our pre-training, our quantization aware training, our fine-tuning. What are the parameters for that? Like we kind of handcrafted them. We tried to figure that out with a black box algorithm, and our configuration actually outperformed it in most points. And like in some points, the black box algorithm couldn't even find something. So in conclusion, we are able to quantize models of our method, which are occupying like the Pareto frontier of model size, including weights and activations against the performance, which is evaluation error in this case on ImageNet datasets, delivering smaller multi-bit networks at higher accuracy. And to the best of our knowledge, this is like the best-in-class results for neural networks with a total memory footprint below 4.3 methods. With the 3 steps I elaborated before, where we have like a tensor-sliced learned precision with hardware vary cost function. We have a targeted gradient modification for weights and activation to mitigate quantization errors. And we have a multi-phase learning schedule to address instabilities in learning arising from updates to learned quantizer model parameters. Thank you so much for listening to me. I hope to see you in person in Hawaii and like to discuss our work even more. Thank you so much. Bye-bye.